Nice. So, hello everyone, and welcome to another Learn and Share session. Today we have Binyi, who has been one of the authors of Protostar, which is one of the latest improvements or papers in the folding schemes landscape. He will be giving us a full walkthrough across the entire protocol. And then we will have like an extensive Q&A session where if anyone has any questions or anything like that, he will be able to respond to any of our doubts. So yeah, I would please ask to not interrupt during the presentation. And then once we go to the Q&A session, Binyi will be able to share also the paper and make notes on top of it or whatever it is so that we can all ask for our doubts and get some replies. So Binyi, thank you very much for attending and joining us and being able to share all of your knowledge on that topic. Whenever you want, feel free to start.
Yeah, thank you, Carlos. Thanks for the introduction. My name is Binyi, and today I'm going to present Protostar, which is a new generic but also efficient IVC scheme. And this is a joint work with Benedict from Espresso Systems. And also, I heard that like most of the audience today are already familiar with a lot of backgrounds. I will only recap background really quickly and focus more on the details of Protostar. So the main goal or the main problem this paper wants to study is to try to prove the correctness of some iterative computations. So you can think about there is a step function f, and we want to prove that some iterative computation executions of f for running many times are correct. So basically there's a one final output and there's an original input, and in each intermediate step we run this f function on the previous input and with some online witness w here. And now more formally, the prover wants to prove that given this final output and the original input, there exists some intermediate witness such that each intermediate execution of the step function is correctly executed. So this model of computation captures a lot of scenarios that can be very useful in the blockchain field, like verifiable delay functions and succinct blockchains like Mina, and more recently, the ZK EVM or ZKVM applications where you prove that certain EVM transactions are correctly executed, which consists of a lot of OP code executions. So that's the background, and to solve this kind of problem, actually already back to 2008, Paul Willems already introduced a really elegant notion called incrementally verifiable computation. So now instead of directly sending all this intermediate witness and to the verifier, and well, verifier just do recomputation, and which will be really expensive. What we do here is that prover will iteratively generate some proofs like this pi m here, given the previous proof and previous input, as well as the intermediate witness here. And after that, the verifier, instead of receiving all this witness, only needs to now receive this final output and this small proofs here and check if it's accepted or not. And if it's acceptable, then the verifier will be confident that all the previous execution are done correctly. So we need that for if the prover are honest, meaning that all the previous prover are correctly generates the computation and the proof, then it must be the case they can actually generate a correct proof that can pass the check. On the other hand, we require that if the verifier can accept some proof, some IVC proof, that means the corresponding prover should actually know the valid witness. This is not just some intuitive definition, but this is the intuitive idea of what the knowledge soundness is. And this is, you see that here we only consider a chain of computation, but more generally, the proof or the computation doesn't need to be a chain. You can consider like a tree of computation, or even more general topology of computation, like a DAG of computation. And this generalization is called proof carrying data, which covers the IVC example. And we know that all the techniques in this paper can generalize to PCD, but for simplicity, let's just focus on IVC in this talk, okay? Okay, so it is well known that this IVC scheme can be constructed from snarks, The idea is just to let the IVC prover to generate a snark proof, proving the statements that the last execution, the last step function execution is correct, and the previous IVC proof is correctly verified by the snark verifier. So this is basically a recursive snark, and the idea is quite simple. However, this kind of scheme is not very practical. The main reason is that first, because of the use of snark, and snark verification is usually not that snark friendly. So it can have a really expensive recursive verifier circuits. And also because of the use of the snark, you might need some like trusted setup or use some pairing-friendly cycles, which might be slow. So given this, many researchers are trying to explore whether it's possible to construct an IVC scheme without the use of snarks. And one of the most popular direction recently is exactly the folding scheme, or the equivalent notion of split accumulation scheme proposed by Nova and another paper, this paper from TCC, which also introduced some very similar notion and some similar results. So what is a folding scheme or a accumulation scheme? The idea is the following. So we have like given some NP relation R, which consists of some like small instance part and a large witness part. The goal here is to try to do the following. So given two different instance witness pairs, we want, instead of directly checking that two instances are satisfiable, we want to first reduce the task of proving two instances into one. So basically we just merge them into a single one, and now it's sufficient to just verify these single instances. And folding is exactly the intermediate step of like merging these two instances. And it consists of the following three algorithms. The first is so-called accumulation prover. Well, given two different instance witness pairs, the prover will try to fold them into a single instance witness pair, X and W. Okay. And the second algorithm is an accumulation verifier, which will check that this folded instance is the correct one. So he will take input of two instances, X1, X2, and he might also get some info, some metadata from the accumulation prover, and check that the output instance is the correct folding instance from these two instances. And we note the highlight here is that usually the accumulation verifier can be much more efficient than the snark verifier. And this is the key reason why the IVC from this can be really efficient. And finally, after folding these two instances with pair, and well, we get a final folded with instance witness pair, the decider will just finally check this XW is inside the relation. So the complete requires that as long as the original instances are satisfiable, the folded one must be also satisfiable. And second is that as long as the prover generates some witness that pass the check, it must be the case that he also knows the original two witnesses for the original two instances. So that's the intuition of the property that the unfolding scheme needs to satisfy. So it is like some previous work like Nova and also BCM LMS 20, they already mentioned like IVC compiler from the accumulation scheme. So I won't talk too much about this part. So the main idea is now to, in the circuits, instead of embedding a snark circuit, you only need to embed an accumulation verifier circuit inside, which is much more efficient and has a much smaller circuit. And that's the key reason why we will have much more efficient IVC prover if we're using accumulation scheme. So because this is not the main topic of our paper, it's already done by Nova and BCLMS, I won't talk too much. But I want to mention one small thing here is that in the IVC verifier, we will run the final decider, which is not necessarily succinct. So it may not be the complexity might be linear to the size of these circuits. So that means we can never guarantee that IVC verifier is like constant size. But this is fine usually because we can delegate the computation of decider to prover as well and add another snark on top of it. And the verification will be still succinct. And this is also mentioned in the Nova paper. Okay, so given this, we already know there's a NOVA and it's quite efficient already. Like I think the recursive circuit only takes like 2 group exponentiations. So why do we want to have a new paper? And the main motivation here is to try to support, for example, ZK EVM application, which we think NOVA is not sufficient yet because of there are 2 missing features there. First is that in NOVA, they are using an R1CS constraint system, which is a traditional constraint system that supports degree 2 gates. However, it's much less expressive compared to some recent advanced gates like high degree custom gates and lookup gates. And while we are writing this paper, we also we also are aware of that there are several follow-ups, like which is really cool. Like Sangreal and Origami, they also say that they can support like Planck and lookup gates, but it turns out that it's not efficient enough if you want to support really high degree gates. The main reason is that if you want to support like degree D gates, the prover and the verifier complexity will be proportional or linear to the gate degree. So there will be a factor of D of the complexity here. That means that we'll cancel out the advantage of using this kind of hydro gates in the first place. So that's not sufficient, we think. We do need to solve this issue. Well, we want to have a IVC prover whose complexity is independent of the gate degree. In particular, the number of group operations should be independent on the gate degree. So that's the first missing feature. And the second missing feature is that for most of the current state of the art, they do not support efficient circuit branching except for a previous work called supernova. So what does it mean? So you can think about in EVM, at each step, usually what you can do is you can pick one of the OP code to execute, right? There are hundreds of OP code in the instruction set of VM. But if we are using Nova, for example, what you have to do is that in the recursive circuit, you have to embed all those circuits for every OP code. And that means the circuit size can be blow up. Like if there are hundreds of OP code, that means the hundreds of factor blow up. So what we want is that we want to have be able to select this step function or this OP code at runtime, but the circuit itself should be only proportional to the size of this single OP code, not the entire set of OP code. So that's the second feature that's missing in the Nova. And we know that these 2 features are exactly very essential and important for having a practical ZK EVM applications. And beyond that, we also note that for previous constructions, they are usually having different proofs, different constructions. It would be great to have a unified framework for that. And our paper is actually trying to achieve both the target and both goals. So first, we have come up with a general recipe for constructing IVC scheme, and more precisely for constructing the folding scheme or accumulation scheme. And in particular, this framework can fold any special sum protocols that is interactive, as long as this special sum protocol is for some certain relation, NP-complete relation. And moreover, besides the modularity, it doesn't sacrifice efficiency. In particular, the efficient Nova scheme is just one very special case in this framework. And after that, we combine this general recipe with several special sum protocols for the relation that we have interest. And after combining that, we can instantiate and construct an IVC scheme that supports really highly expressive gates, like high degree gates, lookup, and the non-uniform computation. And we also note that because of its modularity, it turns out to be very easy to extend to some recent advancement on constraint system like CCS, which is basically a generalization of R1CS to the degree D gates. And one sentence, if I want to remember one sentence, is that in this scheme, the dominant IVC proving cost now is only a 1 MSM of the size of the witness of the computation and a recursive circuit, while the circuit size is dominated by only 3 group operations. So in particular, this 3 group operation is constant. There's no independence, no dependence on the gate degree or even the lookup table size, which is we think is a great feature here. And we also note that there is a concurrent work called Hypernova, which also achieves some similar results. However, we think that for lookup, I think they have to support lookup, they need to work more a lot more, and the complexity is slightly higher. In comparison, our lookup support is almost for free, so that you don't need to pay a lot, like almost negligible overhead for supporting lookup. And on the other hand, in the recursive circuits, in terms of the number of hashes and also non-native operations, we have a factor of log n smaller compared to Hypernova. So that means when the number of gates in this step function can be a lot, the Protostar can be really advantageous. Okay, so that's the background. Now let me come to the meat. I will explain what is the general recipe for constructing folding schemes. Okay, so recall that what we want to do, like what's the goal of the folding scheme, is that given several instances, we want to fold them into single instances of MP relation R. And we follow some framework below. The first step is to build some interactive and information theoretic special sum protocols for this relation R, which turns out to be usually quite easy. And we'll talk about why it is easy later. But before that, let's talk about step 2 and step 3 first. So first, we given this interactive protocol, which is special sum, for which I will explain what special sum means later. Given this protocol, we can transform this interactive protocol into a non-interactive argument of knowledge through some standard tricks, standard transformation. And after that, one of the innovations here is we will have a generic and efficient transform for the NARC verifier of these NARC arguments. And we can build a folding scheme for this NARC proof, okay, which is essentially a folding scheme for the relation R, because the NARC proof is just proving the relation. Some instances are in a relation R. However, this is actually not enough, okay, because we still suffer from the same drawback of Sangria, where the complexity of the prover for high degree gates is large. So given that, we need to add one more step in order to make it efficient for high degree gate support. So what we do is that after having some interactive protocol for relation R, we'll add one more step and transform it to be another interactive protocol that's special sum. However, the set of verifier equations to be checked can be much more compressed and simpler. And after that, we use the same transformation here and obtain a folding scheme for this transformed, or the CV pi here, this transformed interactive protocol. And it turns out the final folding scheme is quite efficient. So even if the gate degree is high, the number of group operations for the prover and verifier are all independent of the degree of the gate, or the degree of the verifier equations to be checked. So that's the general idea. And now let's be more specific, okay? So before going to the transformation, let me quickly remind you what a special sum protocol is. So special sum protocol is some kind of interactive protocol that might have multiple runs. And by K special sum, it means that given K different accepting transcript of this protocol, we will be able to extract from this transcript a valid witness of this relation. And let's take a very, very naive example here, which doesn't quite make sense, but just for illustration. When the prover wants to show the verifier that he knows three witness vectors, A, B, C, such that they satisfy certain head-mod product relation. In particular, for every vector is of length n, and they want to show that for every I from 1 to n, AI times BI equals CI. So what is the protocol? What kind of protocol we can use to prove it? And there's one very straightforward but also naive protocol that actually works in this scenario. So what we do is that we just let the prover directly sense the witness, the ABC vector, and the verifier will directly check that this vector is correct, is valid, by checking all these n equations here. And it's trivial to see that it's actually a one special sum protocol, because every valid transcript is exactly one valid witness for the relation. Okay, and there are three, for every interact protocol or for every protocol, we have three important parameters for this protocol. First is the number of runs, number of prover runs in this protocol. For example, R here equals 1 because prover only sends one time message. So like only sends one round of message to verifier. So R equals 1 here. And second is the maximal degree of each equations being checked by verifier. So you see that verifier here checks n equations, where each equation is just a multiplication. So that means the degree D equals 2 here. And the third parameter is L, which is basically the number of constraints or number of equations being checked by verifier. And here L equals n because verifier are checking n different equations. And you can see that usually for a relation, it's usually pretty easy to construct a special sum protocol for it. The main reason that is easier than directly constructing an IVC scheme for relation R is that first, we don't have any requirements on the size of the communication or the complexity of the verifier. So here you can directly send a really large witness to the verifier, and the verifier can also run a lot of a lot of number of constraints equation check for it. And second, we don't need it to be non-interactive. So this makes the design and analysis of this kind of protocol much easier. So given that, suppose we're already, for some MP relation R, we already have some special sum protocol for it. There's a standard trick to make it non-interactive arguments. The first step is to try to compress all these prover messages, M1 to MR, which might belong to some short commitments using some vector commitment scheme. And we can obtain CR1s to CR. And only at the last step, the prover will open these commitments using the original message, and which is still large. So it doesn't seem quite make sense, but you'll see later why we want to do this. And after having this committed protocol, the prover, the scheme will use the fiat Shamir to make it non-interactive. So basically, instead of letting verifier to generate the randomness, we will use a hash function and generate random challenges through the using the transcript. So now you can see finally we have transformed into non-interactive arguments for the same relation R. Well, the NUC proof or the NUC transcript consists of two parts. The first part is some small parts, which only consists of some commitments and also possibly some challenges. And second part is the original prover messages in the interact protocol, which might be large. And we call it a W, or the proof witness inside of it. So now we already have, for this relation R, we already have a NUC proof for it. And we want to fold a lot of NUC instances. And we have reduced this problem to fold many NUC instances. And you see that this NUC proof has the following format. It consists of some short commitments and short challenges. And also it consists of some long, possibly long prover messages. And this NUC proof is valid or if and only if certain set of constraints or certain set of equations are satisfied. Namely, there are L different equations to be checked. Well, each of the equation are some algebraic degree D formula, which we write it down into D+1 parts, because like this formula might have different terms. Some terms might have degree D, some terms might have degree 1, some terms might have degree 2. So we split them into D+1 parts, where the J's part, Fj, is satisfying that every term in this Fj formula all exactly have the same degree J. So it's quite general. So you can have arbitrary degree D equation, and we just rewrite into this form. Okay. So given this, we want to fold many instances of NUCs. And so we want to first define what accumulator or folded instance means. And that actually is quite similar to a NUC proof. So in the accumulator, we also have commitments, challenges, and prover messages. But there are two key differences. The first is that there's a slack variable here being used, which is also used in Nova. And second, there's an arrow vector commitment, which commit to some length L vector inside. And accumulator instance witness pair is satisfiable if and only if the following set of equations are satisfied. And this is also quite similar to not verifiable check, except first that will pad every term into exactly degree D. So how do you do that? So for every term in Fj which has degree J, we will multiply the power of select variable here, u to the D minus J, so that this term now have degree D instead of degree J anymore. That's the first change that will make it a homogeneous equation where every term is the same degree D. And the second is that for every equation, we doesn't need to be exactly to be evaluated 0. It's okay to have some relaxed arrow here, so long as this arrow vector is consistent with the commitments being committed in this accumulate instance. Okay, so that are the two key differences here. And now our goal is to fold, like suppose we already have accumulator, and every time when we are having a new coming NUC proof, we want to fold this NUC proof into the accumulator to become an updated accumulator. Okay, and so that's the new, as long as the new accumulator is satisfiable, the original two accumulator are also satisfiable. Okay, so that's the problem statement. Let's see how we can fold these two checks and fold these two accumulator schemes. And the idea to solve this problem is to stare at this accumulate check equation for five minutes. But for now, let's just stare for 5 seconds. And you see that key here is that you want to merge these two equation checks so that the new, as long as the new equation check holds, these two equation check also holds. So the natural idea here is to fold them using polynomial interpolation. So what does it mean? So let's consider these polynomials, which looks quite like the accumulator checks, except that for every message, we replaced it with an interpolation or a linear polynomial that interpolates the message in the accumulators and the message in the not verified. For example, the message here becomes x times m plus m prime, while m prime is the message in the accumulator and m is the message in NUC. Similarly, we fold the challenges and the slack variable similarly. So why do we care about this polynomial? The main reason is that the constant coefficient, if you expand it, we see that the constant coefficient exactly matches those equations being checked in the accumulator, original accumulator's check. And the degree D coefficient is exactly the not verified check. So then that means we can use some polynomial identity check later to prove that these two checks are correct. But before that, let me show an example to see why exactly this is the case. So you can believe me more that this is, I'm not lying and this is the case. And let's prove by a very simple example. So let's suppose for simplicity, there's only one equation to be checked. So L equals 1. So all the vectors are with length 1. And the degree D of the gate is 2. And the not verified check is just the R1 plus R1 squared. So that is split into 3 parts, where F0 equals 0, F1 equals R1, and F2 equals R1 squared. And let's see what the polynomial looks like. So we expand this F0, F1, F2 using this linear polynomial, and we expand them and collect them according to the power of x. And we see that exactly here, the constant degree is exactly the accumulates check, where we pad the R prime 1 here using the select variable u, so that every term is exactly degree 2. And similarly, the degree 2 coefficient is exactly the original not verified check. So you might believe me that this property exactly holds. And now let's see how, given this, how we can have a folding scheme. So imagine, like, recall that our goal is to try to check these two equations. First is that the constant coefficient exactly equals this arrow vector being committed in the accumulator instance, and the degree D coefficient exactly are 0. So how to do that? The idea is just to let the prover send a coefficient form of some polynomial, right? And basically, you just want to prove that the polynomial equals this polynomial, and this polynomial is degree d minus 1, meaning the degree d coefficient is just 0, and the constant coefficient is just the vector being committed in the original commitments. So what the prover does is to just first commit all this intermediate coefficient of this polynomial. And we also know because these EJ are actually a vector of length L and they're quite long, so we also need to commit them to make it short. And after that, we can reduce this polynomial identity check to some random evaluation check. And this is just some very standard trick where the verifier just sends some random scalar. And now instead of checking this polynomial identity in order to check these two equations are holding true, it's equivalent to check that this new evaluation check is correct. Basically, you can see this is just another new accumulation check with the same structure, except that every message now are replaced with some linear combination, random linear combination, right here. So U is replaced by alpha plus U, M is replaced by alpha M plus M prime, and the challenge also combined. So this gives us a very natural way to fold the scheme and fold a new instance, where now the prover and verifier just update the message they got. So they'll just update commitments homomorphically and their instance homomorphically using random linear combination. And moreover, prover also needs to update the witness as well, because as we see before the definition, the prover also needs to fold the witness. So this gives us a folding scheme. Well, in practice, what you actually need to do is using fiat-Shamir to make it non-interactive, but this is generally the idea, okay? And also, I only mentioned the prover and the verifier, but decider is trivial. You just, after having some accumulator, you just apply this trick, these checks, and also check that commitments are consistent. So this is the folding scheme. However, this is not efficient enough for a high degree. Why? Because here the prover performs DL group exponentiations, because he has to commit this d minus 1 intermediate across the vector terms, where each term vector has a length of L and there are d minus 1 of them. And similarly, the verifier also needs to apply D group operation in order to fold the error vector commitments using the power of alpha. So that is not very good when the degree D is really, really large, right? Because we have a factor of D complexity here in terms of number of group operations. So we try to solve this issue and make sure that the number of group operation is independent of the gate degree. And let's see how to do that. Recall the reason that we have this kind of complexity is mainly because in every intermediate cross error term, each error term vector has a length L, where L is the number of constraints. You can think about number of constraints if you think about a smart circuit language, but also you can think about the number of equations that verifier check. This can be a lot, right? But what if L is small? Suppose L is small, for example, L is just 1. There's no need to use the vector commitment to commit it to a short element, right? Because it is already a short element. And that means we can just use the trivial identity function as a commitment rather than using the Patterson commitment. So now the goal here is to try to compress these L different constraints into just a single constraint. And how to do that? That's actually quite easy, just using random linear combination again. So for example, let's say there is a verifier who will check 2 equations being holding true. What we can do is that we introduce a new variable beta, which is random, and do a random linear combination of them. And now we have a new equation to be checked now, which is x1 plus x2 plus beta x1 times x2. And it's just a single equation check over the inputs x1, x2, and beta. And more generally, suppose we have L equations over the input of E, M prime, and R prime. We can merge them using the power of beta. Well, beta is a newly introduced variable that is random. Okay. And now we can, like, even if before there are L different checks, now there's only one check being done by the verifier. However, this idea has some issues. First is that the degree of this verifier check is actually much larger, because in the last term, we will multiply this verifier check by some power beta to the L, which has degree L. So the gate degree now becomes D plus L. And L is usually pretty very, very large. It might be even much larger than D. So it makes the scheme even more less efficient. And the second is that all the terms in this check are not homogeneous anymore. For example, because different terms will multiply by different power of beta, so they have different degree. So we can no longer use the folding scheme we had before, because we had the requirements that this check should be homogeneous in order to make sure that the degree D coefficient exactly matches the NUC verifier and the constant coefficient exactly matches the accumulator. But this is actually pretty easy to fix. The idea is to replace all this power of beta by some other different variables, right? So basically, we can make this power of beta by some other messages sent by the prover. And now each beta to the j is just a single variable rather than the power of beta. And now everything will be solved. So this gives us following idea. We are given the original interactive protocol, which is special sound. We add one more round here where the verifier will example a challenge, and the prover will send all the power of beta as his last message. Okay, so basically here bi equals beta to the I, and the prover will send all of them. And now the new verifier check becomes this. We replace beta to the j to be bj, and the degree of this check is just the d plus 1, and every term is exactly having the same degree. So we can now reuse the idea we had before. So you may wonder why we want prover to send these messages. Why not just let the verifier to send this power of beta as some new messages? And the reason is the following. We can definitely let you to do that. However, that will increase the number of elements in the accumulated instance. And usually we see that we want the instance to be short and succinct. So we don't want to do that. Like, for example, to add like OL elements in the short instance. Of course, you can add smaller elements like log n instance, but that also has some other issue in terms of the degree increase. So what we finally choose is to let the prover send the messages. And because the prover message anyway will be committed later using a Patterson commit to make it short elements, so it's fine to be relatively long. But however, as we see, because anyway, the prover still needs to commit one more thing here, one more message here, that means more complexity for the prover. So basically, the prover need to additionally commit to some OL terms here, which can be large because L is usually a large number. But this is also solvable. The idea is that instead of representing a power of beta as a single variable, a single message, we can represent as a product of two variables, okay? For example, for every power of beta, that's beta to the I plus j square root L, we can represent as a product of bi plus beta prime j, where beta prime j is just the power of beta to the j square root L. Okay, so now the degree doesn't increase much. It's still degree d plus 2. But the good thing here is that the prover messages now is much shorter. It's not only square root number of terms here is only square root L. So the commitment complexity is much less. It's only square root L rather than L. And usually it's not very large compared to the complexity that here already pays in the previous rounds. However, so now in summary, what we have done is that initially we have L different degree D equations to be checked. And after this transformation, we only have one degree D equation to be checked. So we don't need to use a Patterson commit for it. However, we also introduce some other checks on the verifier, because the verifier needs to check all this bi and bi prime are computed correctly. So that means we additionally introduce square root L more degree 2 checks for checking correctness of bi and bi prime. But that's actually fine. And the key observation is that all these checks are with low degree, basically degree 2. And that means now finally we'll get what we get is one single equation that has degree D and square root L degree equation that's degree 2. and we can separate them up, like separate them into two parts. And in the one part, we still use the same technique. We will have d-1 cross arrow terms, which every term is just a field elements. And in the second part, we will have a commitment for the intermediate term, which is a commitment, is a group element, but there's only one of them, so it's also independent of the gate degree. I think, is there any questions? D plus K and the case root of L. Yes, exactly. So that's more generally, you don't need to use degree 2. There's one question in the chat saying that you more generally can use degree K, which is correct. And there's a trade-off where the degree will increase more, but the prover complexity can be much smaller. But we found that usually sweet spot is degree 2, so we just set K equals 2 here. Yes, and yeah, as we said before, that now we only need one more commitment here, and add one more separate commitment for the error vector of this length squared L here. And finally, the accumulated verifier only needs to perform R+2 group operations. Basically, this +2, one is exactly the final message that being added, and the other one is exactly one separate commitment for this error vector of length squared L. So when R equals 1, this means 3 group operations. That's exactly the number of group operations in the Protostar. And we note that when we want to support lookup, actually, there will be no overhead. The main reason is that in lookup, there's no high degree gates, and they are all just degree 2 gates. And because degree 2 gates, we can batch them together, right? We can batch all the degree 2 gates together into this additionally introduced gates here. So we don't need to introduce any more cost here. We just need to reuse these commitments, and the number of group operation and accumulated verifier won't change. So that's the main reason we claim that lookup is just for free. Okay, so in summary, the general recipe works as follows. Given some NP-complete relation, we start with some special sum protocol phrase, and we transform into some another interact protocol that has much more compressed check, and for which the checks are much simpler, so we can have a much simpler IBC scheme. And after that, we use standard trick to make non-interact arguments, and we use the trick we mentioned before to construct a folding scheme for that, and use the traditional, like typical classical IBC compiler in the previous work to make an IBC scheme. So that's a general framework, and we've reduced this problem to a much simpler problem now. So basically, the key problem we want to solve is just to give some NP-complete relation, and we just provide some interactive special sum protocol for these relations. And it turns out to be quite easy, actually. In particular, we obtain a one-move special sum protocol for permutation relations, high degree gate check relation, non-uniform circular selection relation, and also CCS relation. And all this protocol all fall in the same trivial pattern. And the pattern is just very similar to the naive protocol we mentioned before, where P just send all the witness, and the verifier just check all this set of algebraic equations corresponding to these relations. For example, in the high degree gate check, what we do is after prover send witness, the verifier just rewrite or recheck all the high degree gates in these constraint systems. And because it's algebraic, so it falls into the category of this special sum protocol. So that's a justification that building a multi-round special sum protocol for many relations are actually pretty easy. However, there's one exception with the lookup relation, because the lookup relation is not algebraic. Basically, given the witness itself, it's hard to represent a lookup relation using a set of algebraic equations over this witness. But it turns out, because we allow the protocol to be interactive, we can actually have a pretty simple protocol for lookup relation as well. And the power is just inside the interaction, and maybe also randomness. So let me quickly recap what a lookup relation is. So here in the lookup relation, there are a list of online lookup values. You want to check that they're all inside some preprocessed table T of T elements. And we are inspired by our previous work by Habok called log derivative for lookup. And it turns out that this lookup relation holds if and only if this sum holds true. That means if and only if there exists some multiplicity mi such that these two sums are the same. And these two sums are just some sum of fractional identities. The first is 1 over x plus wi, where wi is online witness. And the second is mi over x plus ti. And you see basically intuitively, mi is just the number of appearance of ti in this set of wi, and which is also quite easy to compute. So given this, it turns out we can have a really simple 2-round protocols for proving this relation. So in the first round, the prover just compute this witness and this multiplicity and send it to the verifier. And now, once we have already committed all this wi, ti, and mi, again, we are just checking some polynomial identity. And we can use the same trick here. We'll replace this formal variable with some random scalar and check the evaluation identity here. And now the prover will be responsible for computing this fractional identity evaluation and send it back h and g here to the verifier. And now suppose the h and g are computed honestly, then the only check we need to do is just check these two sums are equal, right? This is our some degree 1 check here. But however, we cannot guarantee that it's always honestly computed by the prover. So the verifier also needs to check that all hi and gr are computed correctly. And this gives us some more checks which has degree 2, okay? And given this, we can have a really efficient special sum protocol, and we can have a folding scheme for lookup relation as well. And one great feature of this protocol is that the prover messages are actually pretty sparse. In particular, you see that even though this vector m and this vector g are of length t, but only at most L of them are non-zero. That means when you commit to them, you don't need to pay all the the complexity of t. You only need to do L different group exponentiation in order to commit them into the Peterson commitments. So that gives us way to have a much more efficient folding prover, where the prover only needs to do work proportional to t. However, there's one subtlety here, because in the folding scheme, remember, the prover not only needs to commit all these messages, they also need to compute an error vector, right? Compute this intermediate error vector. And those error vector is actually dependent not only on the not proof messages, but also the original accumulator messenger and original error vector commitments in the instance. And those things are not sparse at all. Okay, so that means you do need to pay like OT complexity for computing the intermediate cross error term. That is not good, meaning that the complexity now is dependent on T. But however, a good observation, key observation here is that what the folding prover actually want to output finally is just the commitment of these intermediate terms. But it turns out that those terms can be updated homomorphically given only the accumulator's message commitments and the accumulator error vector commitments. And those things can be kept track of efficiently. And that means instead of recomputing that vector, we can just directly compute the commitments. And that can be quite efficient. So that's the general idea. We refer to the paper for more details about this trick, okay? And finally, I want to mention that this trick can be extended to vector lookups as well, where each element of the table can be a vector. And this is super helpful for some bit arithmetic circuits like 32-bit XOR or some other bit operations. And is heavily used, I think, in the ZK-EVM applications. Okay, so in summary, we have a lot of special sum subprotocol for some building block relations. And now, in order to obtain a special sum protocol for some NP-complete relation like Plum Cup, we just compose all this subprotocol. That's it. So it's very easy, and it's very easy to analyze as well. Okay, so that's basically it. The key takeaway here is that we come up with a new general recipe for constructing efficient folding schemes. It's not only general, but without sacrifice the efficiency. And on the other hand, we also propose some simple special sum protocol for some expressive relations. And combining these two gives us a protostar, which is an IVC scheme in which the recursive circuit is only dominated by 3 group operations, but it can support arbitrarily high degree gates, can support arbitrarily large lookup tables, and can support arbitrarily many OP codes in the VM instruction set. And that's it. Thank you so much. And now I'm happy to take even more further questions. Yeah, that's it. I see there's another question here. Halo 2's allows you to combine the constant gates. That's fine. Just okay. So in the chat, there's a question called say Halo 2's arithmetization allows you to combine the lookup with the custom gates, but that's fine. Just I see. Yeah, great. Yeah, great to know that. I think, yeah.
Yeah, well, you were saying that the degree of a lookup was always 2, which is not the case in Halo, but it doesn't matter. That yeah, it's still bounded.
I see. Thank you. Thank you for the comments. Okay. Now, Carlos, do I need to switch to the paper, or I can?
You can feel free to show whatever it's helpful to you to explain or to refer to the questions.
Yeah, maybe I can.
Might have.
Okay, maybe I can switch to the paper. I can switch to my iPad and answer any questions.
Perfect. If anyone has any questions, just say it yourself and ask.
First of all, I'd just like you to congratulate you on this work. It's kind of a lot conceptually simpler than a lot of other work on folding. So yeah, this looks really implementable.
Thank you.
I'm enthusiastic about trying that.
Thank you so much. Yeah. Okay. Let me first stop share and then share again. Okay. So this is the paper and this is the slides, and I'm happy to take any questions for now.
Yeah, I could ask one about this selectability of which opcode you use at a given step of computation.
Mm-hmm.
Could you comment on where the cost of having many opcodes to select from appears, or as I make it more non-uniform, what I can do at each stage of computation? Where do I see the cost of that? Oh
yes, so you are saying that suppose the number of opcode is large, right? What would be the cost? Usually that will be migrate to the final decision phase. So basically, I think the cost in the folding step is almost really small, because basically you can see this circuit selection step. You see that this circuit selection, maybe this one is better. Let me show the Protostar. So basically, we change all the checks, original permutation check, to be a sum of check by multiplying some bj. So the degree only increased by 1. So there are mostly the degree of all this equation only increased by 1, and there are some other low degree term constraint you need to add. So I think the folding step is usually quite efficient, because you see that in every step, in every folding step, the witness is still only the witness of a single circuit rather than multiple OP codes. But this equation still is the computation, right? Before we only need to check Wi minus W theta ji equals 0, but now we need to check this sum. But this sum will be absorbed later in the decision phase. That means the final instance witness pair you want to check is more expensive. So that means that this deciding complexity is more expensive. Yeah, so that's the cost being absorbed. But the good advantage here is that in each intermediate folding step, the complexity is not large. It's still approximately the same to that without a circuit selection. Yeah.
Thanks, that's helpful.
Yeah, thank you.
So just to clarify that the decision complexity is still just basically the sum of the complexity of the gates that you have to verify.
Yes, it's kind of like sum of them. Yeah.
Okay.
Whereas the complexity at a given stage is only, I guess, proportional to the largest of the.
Yes.
Okay.
Yes.
Okay.
Yes.
Yeah.
Yeah, I expect you wouldn't expect any better than that. That's pretty much optimal.
Right.
That would be miraculous, I suppose.
Yeah. I think there's another question in the chat. The vector lookup. Okay, Daryl already answered that one. Right, that's correct. How error terms and the slack variable look like after you apply the beta trick. Yeah, so that's basically the same, right? So you see that's, oh, sorry. So there's another question in the chat. Well, how error terms and slack variable will look like after we apply the beta trick. So you see that actually we are not applying that trick before. What we do is, you see here, that the first step is to transform the protocol into a new protocol that apply the CV tricks. So after that, we already have a new interactive protocol, okay, with a new set of equations, and we just use the same trick we had before. Yeah, we had before for dealing with the slack variable and the cross error terms. So basically, you just use the same trick. So whenever you have some algebraic equations, you just pad accordingly to make it exactly the same degree. And now it's just this original set of knock verify check already changes after the beta trick being applied. Is that answering question, Ona? Okay, thank you. Oops.
I can see on that slide that it says ignore public input for simplicity.
Yeah.
Does the public input, how much does that complicate things?
Actually, not very complicated. For example, first we can assume the public input is with constant length using some hash tricks, and then you can just sync it as one part of the instance. So you can check the paper here. Basically, everything is the same except we add public input inside the check. Let me see where is the. Just check one. And check this verify here. You see that in the acc.x, it just adds pi prime here, and everything else is the same. The vector is just adding pi inside, and all the folding is the same. So it doesn't change the complexity much.
Okay, thanks.
Yeah.
Can the PI be unstructured then? So like variable length depending on the IBC step that I am in.
Sorry, can you repeat?
Yeah, can the PI vector be like
PI vector? Oh yeah.
So the public input vector, can it be like variable length independently of the IBC step that we are at?
Oh, you mean the PI? Can PI be variable length?
Yeah, because you said we can apply some hashing tricks.
Yeah, so the idea is that we assume it to be some fixed length, but if it's public length, you can add one more circuit, one more gadget in the original step function by hashing it inside the circuit and just output the hash of it. Right.
Okay. So what does this imply for the folding verifier? Do you also need to include the check for the PI hash inside of it now?
Yes. So basically you just add more constraints for describing this hash. No, but that's not for that's for knock verifier, right? That's not for folding verifier. It's just for knock verifier. Knock verifier okay. can be not succinct, can have a lot of constraints, but the folding verifier is efficient. Yeah.
I see. Thank you.
I had a question about the accumulation verifier. When you compute the alpha, is it possible to I know this system is 30 proof, but would it be possible to use the same hash function for both? Because it seems to me like you're hashing pi.x twice, once in row in arc and once in row ac.
Sorry, I cannot hear really clearly.
Oh,
so you're saying,
sorry, my bad.
okay, yeah.
Yeah, is it possible to reuse the output of row nar? So when the hash function has been initialized with all of pi.x and then kind of chain that with pf, because in this case you end up hashing pi.x twice, once in row with row narc and once with row ac.
So you're saying, can we just reuse a single hash function and also let alpha to be like the sponge?
Yeah, yeah, exactly. Yeah, you'd extract the alpha from the state from having hashed already the pi and pi.x.
I think at least you want to append the accumulation information inside, like example, this acc.x, pi and pi.x and pf. Otherwise, there might be some attack. Like for example, you can reuse some.
I think you can just reorder the argument so that you can compute that that row-ac efficiently as an extension of the row-narc.
Yes, I think for extension, yes, yeah, you can write. As long as you include this information in the sponge, then should be suffice, I guess. Yeah.
Great, thanks.
May I ask a question? Sorry, I missed the front part. I just noticed there's a talk related to Protostar. So I really wonder, maybe that the question is stupid, but what actually is the difference between the Sangria and Protostar?
Oh yeah, so actually I mentioned that in the talk where you see, so I noticed that Sangria also kind of support high degree gates. They have proposed the solution. They even though there's no formal proof yet, but there one key difference between Protostar and Sangria in terms of high degree gate support. So in Sangria, the number of group operations being done by the prover as well as by the verifier is linear to D, to the gate degree D. So basically you have to multiply a D in this complexity. So it kind of actually cancel out the feature or the advantages of using the high degree gates. So you may not use high degree gate in this scenario. You may just use R1CS, which is actually more efficient. However, in this Protostar, we solve this issue, meaning even if you are supporting high degree gates, the proving complexity and the verified complexity for folding is is still independent on the gate degree in terms of the number of group operations. Yeah.
Okay.
Does that answer your question?
Yeah. Could you mention the paper that that shows this method, or it's
of course. Let me. So it's this section compressing verification checks for high degree verifiers. So this is one of the most important section for you to see the tricks here, I think. Yeah.
I see. Yeah. Okay, thank you.
You're welcome.
I have another question in relation to the complexity T that you mentioned at the end, which comes from the fact that apparently there's no possible sparse representation for the initial IVC, put it on some sense. Could you explain it a bit more? Because you seem to say that you will generally pay only for the things that are not zero, basically, which should be L rather than T, but you end up paying T because there's no possible sparse representation for, and I understood the initial IVC instance, which you start, but maybe I misunderstood.
Yeah, so let me maybe first come back to the protocol here. So you see here the folding proof. So folding prover first he needs to compute all the commitments for the prover message in the NARC. That's the first thing, which is actually fun, right? Because that those vectors are sparse, so you can commit them easily using ELK operation. But here the main issue is here is the EJ here, the vector EJ here. You need to compute the coefficient of this polynomial, right? And it's folded for polynomial x plus u d minus j, this one. So the prover needs to compute every vector, error vector EJ here, right? And this EJ is correlated to both the NUX message as well as the accumulator's message. And the accumulator message is not sparse, for example. So that means in order to do the compute this EJ, you actually need to pay like T number of field operations, for example. Right.
I see what you mean. I see.
Yeah, but actually we don't need to
remind us what T was again.
Oh, T is the table size for lookup. Okay. Yeah. But we have a trick that we don't need to compute this vector. You just need to homomorphically update the corresponding commitments. So you never need to know those EJ, and then you can make it much more efficient. Yeah.
Also, if no one else jumps into asking, I will ask another question, which is taking into account that lookups are between quotes for free or at least very cheap. Have you considered to basically try to do wrong-fill arithmetic for the NIF35 and have lookups to actually prove the non-native arithmetic that would do?
That will help. Yeah, because now we are kind of in the constraint system, we can use lookup already, right? That can help with the non-native operation so that it can further improve the circuit size for those non-native field operations. And I think that's another advantage of using Protostar, I think. Yeah.
But so
I think maybe you're asking.
Yeah, I'm asking on internally. Like I'm asking, can you get rid of the curve cycle and instead abuse these cheap lookup properties?
I think even if you are using single cycle, well, you basically now the group operation also needs to do non-native field operations, right? But even if you have lookup, I think that can still be quite expensive because for non-native operations, even if you have lookup, I remember it still takes like 20 or something, 20 for multiplication, for example, for just a field of multiplication. And I do think that the group operation can be really large, might be really large if you don't use cycle curves. I do believe if you're using cycle curves, it's always more efficient because still, if you're using cycle curves, you still need to do non-native field operations for those field operations, but you don't need to do non-native operation arithmetics for group operations. And for those non-native field operation part, you can still use lookup. So that's why I think cycle curves can make it very efficient. But if we are not using cycle curves, only single curve, and then everything should be done in the non-native arithmetic fields. And even with lookup, I still think there might be some blow up. So it might be still, I don't know the exact number, but it's just the feeling that it can be expensive, but maybe it's fun. Yeah, that I cannot say because I haven't experimented it yet. Yeah.
Okay. Yeah, I think so. It depends on whether you've reduced the number of group operations enough that it's still okay to pay that overhead, which is kind of dependent on the exact circuit size and constants and stuff. It's definitely worth experimenting with.
Yes.
I have another question, which is related to like the final decider. Assuming you want to basically collect, you want to basically decide, you have filled your IBC, you have done many folding rounds, and now I want to basically have a snark that it's proving the entire correctness of the IBC. Is there anything that you foresee that is much better than any other stuff to actually prove the sum check in the case that you go that way or whatever because first of all, you have the curves or two IBCs at the same time, one in each side of the cycle. So you need to do double the work. What kind of technique do you think would be the most efficient one, or at least the best one for this final check?
Is the question that is it possible to optimize the complexity for the final check?
Exactly.
When you delegate computation using a snark. Yeah, I haven't thought very deeply on this question, but I think, for example, hyperplonk can be useful in some sense, because like after these CV tricks, right, you can see that the final statements of this decision phase is actually just some commitment opening, right, plus one sum check, because this random linear combined the equation is just the sum check claim, right? So that is really fit and compatible with some sum check based snarks like Spartan or hyperplonk, and that part might be useful if you use hyperplonk. But I haven't think about another question you mentioned, which is a really good question, like how to dealing with these cycle curves of stuff. That's something I need to think more about, I think. Yeah.
So my intuition, and this also simplifies things, is that if you minimize the size of the circuit on one of the curves, and you basically just have it as a wrapper around the other proof, just doing the accumulation, then that turns out, especially for the decider, to be less expensive overall, rather than just treating each curve as sort of equivalent.
You still fall into the issue that if you want to have a pairing-based proof at the end, you kind of need to get the decider, whether you're doing, I don't know, like IPA, sum check, whatever it is, and you need to put that on the other proof so that you verify not only the decider, but actually the other proof's decider natively inside of the pairing proof. I don't know if that makes sense.
Well, remember that if you're using pairing-based curves on both sides, then that ends up being really expensive, because
usually
I meant half pairing.
But
half pairing
800,
cycle.
yeah, half pairing, yeah, that will probably work.
Yeah, half pairing is fun, and I don't quite understand what you mean by you have to prove the pairing circuits. You don't have to prove any pairing circuits in the final step, right?
No, definitely. What I meant is, if at the end I want to have a snark that it's proving the IBC accumulated in both parts of the cycle, I let's say I have two IBCs to actually prove inside of a snark.
Yeah, finally, I think you will have two proofs, right? One is
exactly. But if I want to put that, for example, in the EVM or something like this, what in reality I want is to have one pairing-based proof. So I don't know, use growth or whatever it is. And
yes, that's one way.
Exactly. Which will work, for example, with their curves, Pluto Eris, for example. Really nice.
Yes. Yeah, I think that's one approach where you have two proofs first, and then you aggregate again using gross, so that you can put it on EVM on Ethereum. Yeah.
But by the way, Pluto Eris are quite conservative, because I went with I think it's 400 and something bits. So it is possible to do it in a smaller curve. I was trying to go for strictly 128-bit security, but if you're happy with BLS 12 381, then you can get away with something smaller. I should really do the work and propose a concrete curve for that.
Looking forward.
And maybe finally, at least from my side, and I will shut up. The last question that I have is it's related to the composition that we had at the beginning. So inside of folding schemes, we lose privacy, right? Against other solutions like split accumulation, for example, because we need to basically send our witnessing clear so that we can fold on the top of it on every single round in the IBC. My question is, do you foresee, or which are your thoughts on, for example, committing to the witness and then doing some kind of delegation of the proving in the cloud, for example, so that we can enable mobile phones or devices like this to actually use folding schemes on a much easier manner?
Yeah, that's something I actually have thinking about. So the intuition here is like, for example, instead of doing committing, what I'm thinking is that you can do some secret sharing over this witness over multiple servers. And I believe that it can be quite efficient because all these operations in the folding step is actually pretty linear, right? Just some randomly combination. So it might be, I think it can be quite efficient. And the assumption is that over these servers that secretly share this witness, like a majority of them are honest, then you can guarantee that this witness will like never reveal any information of the original witness. Yeah, that's
exactly.
Yeah, that's intuition. Yeah.
Thank you. Thank you so much.
Yeah. Thank you. Okay. So...
Does anyone have any other questions or
I have one more. I'm sorry. Maybe you also like answered this previous in the talk, but will the recent Nova attack affect Protostar also?
I think no, because the Nova attack is mostly about the IVC compiler. We are just using that as a black box. So you can use the new paper from Dan Bonnet and Wilson, that compiler for IVC. So like this paper is only talking about folding scheme or accumulation scheme, and we just use the IVC compiling black box. So that won't affect the Protostar as long as you're using the right IVC compiler. Yeah.
Which paper you mentioned?
There's a new paper that's exactly mentioned the attack for Nova. Is I think the name is Revisiting Nova, right?
Yeah, Revisiting Nova. Yeah.
Yeah, that paper already mentioned an IVC compiler. Like you can just use that compiler there. So basically, the compiler means that given some folding scheme, how we can construct a secure IVC scheme, and we can reuse that in Protostar as well. Yeah.
Got it.
Do you know if that generalizes to PCD in the same way?
You mean, so first,
so the paper that fixes the problem with Nova, does it go into any detail about how you would apply it to PCD?
I don't know, because I think Nova only works for IVC, right? They don't mention any compiler for PCD. Only the PCC paper, the BCLMS, they have a compiler for PCD, but that is less, I guess it's less efficient than the Nova one. But Nova doesn't mention anything about PCD compiler.
It's probably relatively straightforward, but I think it probably deserves a paper and properly formalizing.
Yeah.
This was part of the issue, right? In the paper, there's no mention to or no formalization on how the IVC should be done with the curve cycle. So they based the paper on the implementation bug, if I remember correctly.
Yeah, this has been an issue with a lot of papers, that there's a little bit of hand waving about how to apply it to curve cycles in a lot of these papers. Yeah, so it really someone has to do the work of implementing it and then writing up what they've implemented.
I had one final question about implementation. If you were to implement it, would you go for the current like Espresso systems type backend? What would be the best place to start?
That I don't know. There are many backend which are all pretty good, like Jellyfish from Espresso System and ArcWorks, and also maybe even more others. I think I'm not an expert on this. I'm not authoritative to say which one is the best, but I think both Jellyfish because Jellyfish has some implementation of Hyperplunk, and also know the PSE, the Serum Foundation, they already have some really good implementation about it. I don't know if it's open source yet though. Like Colors, maybe you can add more.
It is. It's under Bunz Binyin repo, and it's based on the ZK crypto primitives. So that also gives it a bit more variety, basically.
Awesome.
Okay, so if no one else has any questions, I will thank a lot to Binyi for coming here and explaining to us how Protostar works and answering all of the questions. Thank you so much in the name of everyone. And yeah, hope to see you soon in another session with another great paper like this one.
Thank you. By the way, I also want to echo the comments Nico made. I think like the attack mentioned is just mostly about the some flaw vulnerability of the implementation. Yes, and I think the paper is all right. Yeah. Okay. Thank you. Thank you so much.
I mean, maybe the paper should have gone into more detail about that.
That's true. That's also true. Yeah. Yeah.
Yeah, because when things like that are missing from papers, that's when you get attacks because people get them wrong, including the original authors. Authors get them wrong.
Yes, totally agree. Yeah.
Nice. We will leave it here. Thank you, everyone, and especially Binyi for the time. And
Thank you.
chat to you soon. Bye-bye.
Thank you, Sue. Bye-bye.
Bye.